Hey guys, welcome back to my channel. So in today's video, we'll talk about activation functions. Activation functions are one of the most important things when you set out to build neural networks, because activation functions are the one that provide you nonlinearity, and that is what is the core principle of why neural networks are able to estimate complex functions and functions of higher degree order also. Right, so in today's video we'll only talk about activation functions. We'll see in total about 8 activation functions. We'll also discuss in what scenarios and what use cases you should use which activation function, and we'll also see the mathematical representation or plotting of these activation functions, how they actually look when you plot them on a graph. So let's get started. So the first thing is that activation functions play a very crucial role in deep learning models. They introduce nonlinearity, enabling neural networks to learn complex patterns and make accurate predictions. So what it is said that if in between two linear layers, if you introduce just one activation layer, right? Just one activation layer, which is obviously a non-linear activation function, then you can theoretically approximate any continuous function of any degree, right? You just have to keep making this linear layer larger and larger, and you can approximate any function, any order function. It has to be a continuous function. That is the only condition, and this is basically known as universal function approximation. So activation functions play a very important role because they only introduce nonlinearity, and as I said, that is the only power of a neural network to basically estimate complex non-linear or complex higher order functions, right? So let us start by talking about the first activation function. This is the linear activation function. So linear activation function is a simple linear function. It basically returns the input as it is, right? So this is the linear activation functions where fx is equals to x. It is commonly used for tasks like linear regression, linear classification, and all those tasks where a linear model is required. So a problem statement where linear classifiers are helpful is when you have to predict a price of a house based on features like area, number of rooms, locations. This is a general linear regression problem where you have n number of features and there is a linear correlation between these features to predict an output value, which is the price of the house. So if you plot a linear function, this is how it would look. Linear regression models are a subset of models, but it is a very powerful class of models for a very trivial task or smaller task. These linear regression models or linear models have been seen to perform extremely well because they are able to correlate or find the correlation in the data extremely well, right? And it's a very general rule that if you don't need higher computation or higher complexity, then you should not go to higher complexity. You should try to find out if you can solve your problems by using these simple models like linear models. Next function that we'll talk about is the sigmoid activation function. So the sigmoid activation function is widely used in binary classification problems. It maps input values to a range between 0 and 1. This is very important, and thereby providing a probability like output, right? So this is your sort of mathematical definition of the function, which is 1 upon 1 plus e to the power minus x, right? So this is your sigmoid function, and as the definition said, that sigmoid functions map the value between 0 and 1. So, and what is between 0 and 1? Probabilities. So this basically is like mapping your input to a probability, and that is why wherever in problem statements where you need probability like outputs, sigmoid function is a very good option or a very good choice to use, right? So for example, predicting the likelihood of a customer subscribing to a service based on a demographic or a behavioral data. So based on demographics and behavioral data, what is the probability or likelihood that the customer will subscribe? So the answer more or less will be between 0 and 1, right? There will be a probability between 0 and 1. Either the user will subscribe or will not subscribe, depending on what probability comes out as the output, right? So in scenarios where you want probabilistic outputs, single probabilistic outputs, sigmoid function is a very good choice to have. And this is your plot. This is your plot for sigmoid function, right? So the next function that we'll talk about is your hyperbolic tangent or TanH function, right? So hyperbolic tangent or TanH is very similar to sigmoid function, but it actually maps the value between -1 to 1 rather than from 0 to 1 like in the case of sigmoid function. It maps the value from -1 to 1. And this function is used in hidden layers in neural network as an activation function. This is a very famous activation function and was used very widely before the introduction of a ReLU activation function. So this is used in a lot of neural networks, training a lot of neural networks. This is the definition of the TanH function, which is e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x, right? So that is your hyperbolic tangent. This is a common mathematical function. The fact that it maps the input value between -1 to 1 basically allows it to have some scope for negative emotions also, right? For negative representation also. So therefore, in tasks where you have the problem statement where you want to capture both the positive and the negative sentiment, this is a very good activation function to use, right? So for example, sentiment analysis is a classic example where TanH can help. So sentiment analysis in NLP, where TanH helps to capture both positive and negative sentiments, because in sentiment analysis you have three kinds of sentiments. One is your negative sentiment, then your neutral sentiment. So one is your negative, then one is your neutral, and then one is your positive, right? So you want to capture all three of these sentiments, and there where you have this type of problem statements, TanH is a very good option to use, right? So this is your how the plot of TanH function, a TanH hyperbolic tangent activation function looks like. Now let's talk about ReLU. So ReLU is, I think, the most popular activation function. ReLU stands for rectified linear unit. And as a rule of thumb, if you are not able to identify which activation function you should use for your problem statement, ReLU becomes the de facto activation functions, because it is seen that it performs almost as good as any other activation functions, even better, and for all use cases, right? So if you're not able to decide what activation function you should go to, you should always go to rectified linear unit, which is ReLU. So this is one of the most popular activation functions. It returns the input directly if it is positive. If the input is positive, it returns the input directly. Otherwise, it returns 0. So it's a very simple, this is the mathematical definition of ReLU, right? So this is just a fancy way of saying max between 0 and x, right? So one of the major advantages of ReLU is that before ReLU, we had a very big problem of vanishing gradient. So when you backpropagate your neural network, if your gradient is very small, as you pass through the layers in backpropagation, that gradient will become smaller and smaller, and ultimately it will diminish to a value that it is mathematically insignificant, right? That is the main problem that ReLU has been able to solve, because the derivative is either 0 or 1, right? So it does not diminish as you go back in your neural network, or you traverse through the layers of your neural network while propagating your gradient, right? So this is one of the most advantageous property of ReLU activation functions, and that is why it has been very popular in almost all tasks, especially in image classification, because this was a field where vanishing gradient was the problem that was much more pronounced because of the complexity and the higher dimensionality in which we operate in. So ReLU helps you to learn discriminative features. So for example, in image classification problem, we have a lot of dead pixels in an image. So for example, if I draw an image and the object that I want to learn is only in the center of the image, right? So all this area that is outside this are dead pixels, right? This is not I want to learn. So ReLU basically will make the neurons that are hitting at this part of the convolution as 0, and for convolutions which are hitting at the area where there is actual object, the neurons will fire, right? So that is why 0 and 1 combination actually works, and this has been very helpful for computer vision tasks. So as I said, ReLU can be your default activation function. This will work more or less in every use case, but if you are more inclined to use the most appropriate activation function depending on your problem statement, then it is important that you know all varieties of the activation functions and choose the one that suits your problem statement the most. So now let's talk about the variations of ReLU. So the first variation that we'll talk about is a leaky ReLU. So one of the problems that came up with ReLU was that for value less than 0, the ReLU activation was completely 0, right? So this created a problem of dead neurons that never fired. So for example, while your gradient descent, you are supposed stuck here, right? Then basically this is a dead spot, right? You do not have any incentive of moving towards the right, you do not have any incentive of moving towards the left, right? So there is no way to know how you should optimize or where should you move, right? So that is why a leaky Relu, a variation of leaky Relu was variation of Relu was introduced. Let us see what it is. So leaky Relu is a variant of Relu that allows small negative values for negative inputs, right? This is the key important point. It helps to address the dying Relu problem. Dying Relu problem means that once you are here, you are almost on dead neurons. You cannot do much to optimize your performance further, right? So where leaky Relu comes into use, object detection in computer vision is something that leaky Relu is good at, because leaky Relu helps identify objects with varying level of illumination. So what does that mean? So a lot of the times in computer vision, we do not have illuminated brightened images, right? And this is very common, right? Whenever you click an image, suppose you are clicking an image in the night or when the sun is not very bright, right? So, or even if the sun is bright, there is a shadow falling on an object or something like that. So whenever the illumination of the image is not very strong or is not very high, the pixel representation of that area will be negative pixel representation, right? It will be a negative value. So for example, in this, the image of the boy or the person is highly illuminated, but here assume the image of this tree is very less illuminated. It is having negative pixel values, right? So if we use Relu, this basically will become dead pixels and this will be 0, right? It will be as if there is no object here, but that is not the case, right? We know that there is an object, but there is very less illumination, very less light on that object, and that is why it is not very pronounced in the image. So we do not want to miss out on these objects, or we do not want to we want to correct for this. And that is the reason why leaky Relu was introduced, where even for x less than 0, you have a certain value, right? You have a certain small value which tells you that there is some object there and helps you identify that object, and you do not completely discard the presence of that object. So how is that Relu defined? So for x greater than 0, it is x, just like Relu. But for x less than 0, it is alpha x, where alpha is a very small constant. So even if you see in this plot, it might not be very visible, but this line is not completely straight, right? So this is the line, and a straight line would have looked like this, right? So there's a very small curve for x less than 0, and you do not have completely 0 values for x negative, right? So this is where leaky Relu comes in for objects, for images where you have contrast or high contrast or difference of illumination between different objects of the images. So the next variation of Relu is a PReLU or Parametric Relu. So let us understand what that is. So Parametric Relu is actually a generalization of leaky Relu, where the slope of negative values is actually learnable. It introduces a parameter to determine the slope for negative inputs. So previously what we saw here, that this alpha is a constant. This is more or less something that we supply outside of the model. It becomes a hyperparameter. Whereas in Parametric Relu, what was seen, that if you let alpha be a learnable parameter, then certain category of tasks, such as your automatic speech recognition, improves a lot. And if it makes a learnable parameter, it is able to identify different kind of speakers. So let us understand this in a little more detail. Whenever there is a automatic speech recognition task at hand, right, where multiple speakers are speaking and you want to recognize the speech of each and every speaker. Now every speaker might have a different energy level, might have a different way of delivering content, might have a different accent, might have different length of pauses, different length of pitch and everything, right? So every speaker is very different. Voice is almost like a fingerprint, right? Everyone has a different voice to a certain extent, right? So if I fix my alpha, which is the parameter that was fixed in leaky Relu, then I will not be able to capture the difference in all these attributes of a voice of different speakers. Whereas if I make my parameter as a learnable parameter, then the model's capacity to capture varying speech patterns improves a bit. There is a way to prove this I'm not sure if there is a way to prove this mathematically, but this is something that has been seen empirically, right? While training models, we saw that if you made this a learning variable, a learnable parameter, then the automatic speech recognition tasks, the accuracy of these tasks increased a lot, and that is why parametric Relu is something that is now widely used wherever speech recognition or speech related tasks are used. So how is parametric Relu defined? So it is exactly similar to Leaky ReLU. Here only alpha, instead of being a small constant, is a learnable parameter. So instead of being just a static value, this is learnable, and as the model grows or evolves, it learns a better and better value of alpha that helps it to achieve a more accurate representation of the task at hand, right? Now, the final variation of Relu that we'll talk about is exponential linear unit. So let us see what exponential linear unit is. ELU is a smooth approximation of Relu for negative inputs. It handles negative values gracefully and helps to prevent dead neurons. So whatever we saw earlier was, whatever variations we saw of Relu earlier, we did not see a smooth progression of your negative neurons, of the negative value where the activation function is negative. We did not see a smooth progression. Whereas in ELU, that is the case, where this progression has been made smooth rather than being a very unsmooth sort of an progression. This has been made a very smooth progression, and one might wonder why that is the case. So there are few things that ELU helps when compared to Relu or different variations of Relu. It basically stabilizes your training process, right? Because the gradient, when gradient flows back through the process of backpropagation, there are less chances of diminishing gradient or gradient not propagating back properly, and that is why this smoothness is introduced in the activation function. This is true in every case. If your activation function is more smoother, then your learning will be more stabilized, will be more better, and will be more predictable, right? So this is nothing new that happens here, but I think this is something that was witnessed later in case of rectified linear units, that if you make this progression smoother, you are able to perform even better for certain type of tasks. So let us see where Relu sort of ELU helps. So ELU, the main application of ELU that we have seen is in generative adversarial networks. Generative adversarial networks use ELU because it helps in generating realistic images. So what does that mean, right? So let us first very briefly understand what are generative adversarial networks. So it is basically a two-party model where you have a generator and a discriminator. Discriminator is sort of you can think of as a cop, right? And this is a fraud person. So what the generator tries to do, it is trying to imitate something which looks like real but is not real, and then the discriminator's task is to tell whether the image that generator has created is actually real or not, right? So, and the generator and discriminator both work in tandem. They improve based on each other's generation and decisions, and then comes a time when the generator is so good, you can throw away the discriminator, and the generator is so good that you input noise to it and it can generate perfectly valid art, right? Or very good looking art, as if it's a real artist who is drawing this image, right? So that is what a generative adversarial network is. ELU helps GANs to fight something known as something which is basically means that GANs are not able to explore the entire distribution of your target dataset, right? Which is known as the mode collapse. What does that mean? That to generate images from the entire spectrum of the target distribution, you should be able to explore the entire spectrum, right? And that is where it was seen that if you make this progression smoother, it gives the generative adversarial network more liberty or more ability to traverse the entire spectrum of where it can move and generate images, so that it can draw better and better images, right? This again is more of an empirical evidence that was seen, and that is why exponential linear units have been very successful when it comes to generative adversarial networks. How is an ELU defined? So this is a very simple definition of ELU, where it is again x when x is greater than 0. So for all variations of rectified linear unit as well as exponential linear unit, we see that it remains x for greater than x if we are greater than 0, and for less than 0 it is basically this exponential value, which is alpha e to the power x minus 1. So there is an exponential term here which ensures smooth progression of the curve as it crosses that x equal to 0 boundary, right? So this is all about exponential linear unit. The last activation function that we'll talk about is your softmax activation function. So softmax, more than an activation function, it is actually something that helps you when you have multi-classes or multi-class classification problem at hand, right? Because what it does, it converts a vector of real numbers into a probability distribution. And what also it does it, that even if in that real vector, if the difference between the values is not very pronounced, the output of a softmax functions will ensure that the differences, even minimal differences, are sufficiently pronounced so that your model is very confident while outputting a particular class, right? So softmax function is often used in multi-class classification problems. It converts a vector of real numbers into a probability distribution over the classes, always ensuring that the sum is equal to 1. So obviously if it's a probability distribution, the sum has to be 1. So where it is helpful, right? So for example, if you have a task of identifying what digit it is, right? So you can have like 1, 2, 3, 4, and you basically have 10 classes, 0. So, and you have to, and you are basically fed an input. So basically if I fed an input like this, then I have to predict what that image is or in which class this image falls, right? So this is where softmax functions come into play, because the value of, if you look just by image comparison, a value of 4 and a 9 might be very close, because there is only a single curve that is missing while you create 4 and 9, depending on how you draw these images or how your data set is actually drawn or created. But these values will be very close, and if you just predict based on these values, then it will basically say that I am like 30% confident that this is 9, and I'm like maybe 40% confident that this is 4, and then rest 30% goes to some other classes as error, right? But what softmax will do is it will pronounce this difference, that this is 4, only there is a very less difference in the real values, but as soon as you pass it through the softmax function, the probability distribution will come out in a way that it will say that x, I'm 80% confidence that this is 4, right? So that is what you want when you have multi-class classification, because you want to confidently take your decision. Either it's a wrong decision or a right decision, but you want to have some confidence so that you can learn and improve based on those decisions, right? If you're always confused between different classes, then the learning will not happen, and it's a very difficult situation to be in. So the confidence is very important when you are using multi-class classification problems, and that is where softmax function activation functions comes into play. So softmax is generally the almost always is the last layer of your network, right? So whenever your entire network is done using activation functions that we previously discussed, and in the end there will be a softmax function when you have to define a particular class for your input value. How it is defined? It is basically an exponential of e to the power x of I upon summation of e to the power x of I from 1 to n, where n is the total number of classes that you want to predict on, right? So this is your softmax function. This is the last activation functions this is the 8th and the last activation function that we wanted to discuss. So let us quickly conclude. So activation functions are essential in deep learning models as they introduce nonlinearity, as we already discussed, and allows neural networks to learn complex patterns. Each activation function has its own unique properties and in use cases, and therefore there are certain use cases where certain activation functions are helpful. But as a general rule of thumb, if you cannot find out in what situation what activation function you should use, you can always fall back to ReLU. ReLU works in almost 99% of the cases. However, if you want to have a more effective training process, if you are very concerned about your training and the choice of your activation function, that you have to understand your problem statement very correctly, because choosing the right activation functions can impact the performance and effectiveness of your deep learning models, right? So it is an important decision, but it's not very critical, because when you use a ReLU as an activation function, it has been seen that it almost works in all of the use cases. But when that is of essence, when you have exhausted all other your resources to improve efficiency, all other tools that you have to improve your efficiency of the model, then a choice of activation functions becomes an important decision, and you should take that very carefully. So thank you so much for watching. Please do not forget to like and share this video, and please do not forget to subscribe to this channel. I'll keep on coming with more interesting videos on deep learning like this. Thank you.